Okay, so we are in generalized linear models with examples in R. We're in Chapter 2 and question 2.2. And what we're asked to do here is, in the setting of simple linear regression, we're asked to derive expressions for beta naught and beta 1 using the fact that the partial derivative of the sum of squares when set to 0 will we can work those expressions to eventually arrive here. Okay, so if that wasn't clear, we will work through these. And as we go throughout, there's going to be these expressions of x bar and y bar that are where x bar is going to be the weighted average of x and y bar is the weighted average of y. Okay, so let's start here. So let's remind ourselves of what the function s is. It's just the sum of squares, and this is the expression for the sum of squares. It's the actual value minus the predicted value squared, and then we sum all of those, hence the sum of squares. And because mu here, the expected value of y, is just our linear predictor, I can rewrite it like this. Okay? And so now if I take the derivative of this, I just saw a mistake here. Let me fix it. Okay. So anyway, so if I take the derivative of this expression, so I take the 2 out front, and then you take a derivative, and so we should arrive at these expressions right here. So I have a negative 2 out here because, well, beta 1 and beta naught are actually negative, and I think at the book they don't put a negative, but it's not going to matter actually. Okay, so and you'll see why here in just a second. Okay, so the proposition here is that if I set the partial derivative of s with respect to beta naught, if I set that equal to 0, I will arrive at the expression that we're told we'll arrive at. Okay, and so that's what we do. The reason it doesn't matter if it's positive or negative 2 here is the first thing I'm going to do is I'm just going to divide both sides by 2 or negative 2. And because I'm dividing 0 by that, I'm just going to come out with 0. So anyway, so this first expression where we're trying to find an expression for beta naught is the simple one. Okay, so I don't know that I'll go through this, but basically all I'm doing is expanding everything, right? I'm distributing sums and distributing y's until we get to an expression where beta naught equals the weighted mean of y, which is this, minus beta 1 times the weighted mean of x. Okay, and that gives us this. That's the expression that we're trying to find. Okay, so you can go through the math for yourself. Okay, now the second one is actually pretty tricky up to a point. So to get from here to an expression for beta 1 is not difficult. But we arrive at, well, if you go through the way that I did it, you arrive at something that doesn't look like what we want it to be. But, so let's go through this. So we have our partial derivative of the sum of squares with respect to beta 1 is this, or I think there actually should be a negative there, but again, it doesn't matter because we're going to divide both sides over by 0. And we're left with this expression. Okay. If I distribute the negative, I get this expression. Okay. And now I'm going to distribute the sum of w sub I, x sub I over everything. Okay, so w sub I, x sub I times y sub I, and I get this, times beta naught, I get this, times beta 1 xi, I get this. Okay, well now the beta naught term and the beta 1 term are constants, and so these can come outside of the summation. Okay, because there's no unique values for I, right? It's the same for each value or for each term. Okay. So I'm going to bring those out front. So now I have the same expression. The first term is the same. I'm bringing the beta naught out. Okay, so there it is right there. And I'm bringing the beta 1 out. And now notice that I have two x's here. And so I just have xi squared. Okay, so I've just been simplifying things. And now I have beta naught, but I already derived an expression for beta naught, which is here. And so I'm going to substitute that in. Okay. And so now this is our expression, expanded. Now, I'm trying to solve for beta 1. And I have one term with beta 1, well, actually two terms here, and then another term here. Okay, and so I'm going to get these on the same side as the equal sign. Okay, so remember, all of this up to this point is equal to 0. Okay, So I'm going to just add all of this over to the other side of 0. Okay, so now I have this expression, which was right here, plus this expression, and I add it over and I get this, and I get this expression. Okay. All right. So now the next thing I do is I'm just going to multiply through this parenthetical term. Okay. So now I get y bar times the sum of wx, and then I get beta 1 x bar times the sum of wx, and then I have beta 1 times wx squared, and again, all of that equals this. Okay. Now, again, I'm trying to find a term or an expression for beta 1, and I have two beta 1 terms here, so I'm just going to compile all of this together. Okay. So I get beta 1 is equal, or beta 1 times this guy, okay, minus this guy. Why a minus? Because we had this minus here, right? So, so if I were to expand this out, I would arrive back at this expression. And then this term right here, I'm just going to subtract over because it doesn't have a beta 1 in it. Okay, so I'm just going to get it over to the other side. Okay, so now I'm left with this expression. Okay, and now finding any expression for beta 1 is simple, right? I just divide both sides by this parenthetical term. Okay, and that's what I get right here. Great. So we have an expression for beta 1. However, this expression for beta 1 does not look very much like what we're actually trying to find, right? So the numerator for the expression that we're trying to find looks like this, but we have this, okay? Those look pretty far apart. And the denominator that we're trying to find should be this, but we have this. Again, they don't look very close. And so what we have to do is set about demonstrating that this numerator is equal to this numerator and that this denominator is equal to this denominator here. Okay. And so that's what we'll do from here on out, or you can just stop. The expression is true. This is just really a practice in arithmetic that was very tedious. But so let's first start with the numerator, okay? And so one of the things that we want to recall here is our expressions for x bar and y bar, okay? They're the weighted means of these things. And so then this implies that if I just rearrange these, I can get an expression for w, the sum of w and x equals x bar times w, right? So if this expression right here, if I just multiply both sides through by the sum of w, then I get that x bar times the sum of w equals the sum of xi, wi xi, and same thing goes for y, okay? And so we're going to use that. So this is the numerator that we derived already, okay? So I have all of that. And so now I'm just going to rewrite this term right here according to what we were just showing, okay? So now I have y bar times x bar times the sum of w, okay, the weights of w, okay? So now I notice that I have a sum of w in both of these terms, so I can collect the terms here, okay? And so now I get this xi and this x bar, y bar, okay? Well, this expression right here can be written as this right here, right? So we have a xi minus x bar, and then I can just assign one of these yi and the other one y bar, okay? Now it turns out that this expression right here, this expression right here equals 0. And just to give a quick sanity check why that should be, so forget the fact that we have weighted sums here that kind of makes it, or like weighted averages and weighted sums, that makes it a little bit more difficult to think about. But if you just think about a normal mean, if I were to take the deviations away from the mean and then sum all of those deviations, I would come up with 0. And in fact, that's why in least squares, the algorithm, we don't take just the deviation, right? Because when you sum all of the deviations away from the mean, you get 0. So we square it for that exact reason. Okay. So in any way, this second term here all goes to 0, and then we're just left with this. Okay. Well, that is the numerator that we're looking for. Okay. So what we've showed here is that the numerator for the expression that we derived for beta 1, which is given by here, is actually equal to the target expression. Okay. That's fine. All right, so now we need to move on to the denominator. Again, here's our denominator, but it should look like this, or that's our target anyway. So, okay, so so we're going to use a property of summations, and that property is just the following. So if I take the weighted sum of all of the instances of a variable, v, where v is like x or like y, I can just rewrite that as the mean of that variable, or the weighted mean of that variable, times the sum of the w's. Okay, and so you can do this on pen and paper to prove to yourself that that's true, but that's the case. Okay, so we're going to use that as we go forward here. Okay, so so again, this is what we started with right here, all of that. Okay, now I'm going to rewrite all of this right here. I'm going to rewrite all of that like this. Okay. So so this term matches this term, and I'm going to mess with this term right here. So I have that original x bar, and then I'm rewriting all of this, and I rewrite that as x bar times the sum of w's. Okay. Well, x bar times x bar, well, that's x bar squared. So now I have this expression, and now I can just collect terms under the summation of w's, and I get this expression. Okay. Well, this is really, really, really close to the thing that we're trying to arrive at, okay, but it's not there yet, right? So this has x minus x bar, and then that difference squared. We have x squared minus x bar squared, okay? So what we need to find, and what we will show, is that this is actually equal to this. Okay, so now in order to do that, I'm going to cheat just a little bit, but I don't think it's a big cheat, because this is a well-known algebraic result, or whatever you want to call it. I'm not really up with the math lingo, but so instead of trying to get from here to our target, I'm going to start at our target and show that it's equal to this. So that's why it's a little bit of a cheat, but I think it's permissible in this case. So here's our target. This is what we want to get to. And what we're going to arrive at is the expression that we already have. So in other words, what we already have is equal to our target. Okay, so to do this, I'm just going to start by expanding this parenthetical term, because I have two of them, right? So I just have two of them now. Okay, and now I'm going to expand that, right? So x times x times x bar times x bar times x bar. Okay, and so I get this expression right here, hopefully, if I have done everything correct. Okay. And so now I'm just going to distribute the sum of w's over all of that. Okay, so now I get sum of w x squared minus 2 of this guy, right, plus this. Okay, so I hope you can follow along if you pause this or go to the Colab sheet. Okay. All right, so now I'm just going to take the constants out of the summations. Okay, so so here the 2 is already outside, but the x bar is a constant, so I have now 2x bar is outside, and I just have what's not a constant. And then similarly, for this last term here, x bar is a constant, or x bar squared is a constant, so now I have this. Right, so this is our updated expression right here. Okay. All right. So now I'm going to again rewrite this. I'm going to rewrite this as x bar times the sum of w's. Okay, so now I have this term, and everything else is the same. Okay. Well, now again I have two x bars. Well, that's just I have the product of x bar, and that's x bar squared, right? So now again I have this expression. So I have w x squared minus 2x bar squared plus an x bar squared, and they're all trailing the sums of w's. Okay, so now I'm going to collect everything under the sum of well, I guess not yet, but anyway, so let's see here. Okay, so here I have negative 2x bars, and then I have 1x bar, right? So altogether, when I take 2 away from the 1, I have a negative x bar. Okay, so that's what I have here. And now I can collect everything under my w's, and I arrive at the expression that we found, kind of, after some cajoling here, right? So again, what we've showed is that our target is equal to the thing that we found here, right? So now we can write all of this again, and we get that beta 1 or beta 1 hat, or our estimate, is equal to this, right? So we've derived the numerator and the denominator, and that's what our target expression was in the very, very first place here.